Okay, so then we would literally have to add up each of these numbers. So 216,000 plus 86,400. Oops. Let me try that again. 216,000 plus 86,400 plus 3,060 plus 10 would be 305,470. Is literally what that number would translate to in our common numerical system. Okay, the Mayan culture, sort of a little interesting in how they went about coming up with their numeration system. I guess we can say, sort of base it on base 20. One thought would be they looked at their fingers and toes and realized they had 20 of them. And so, kind of like the other culture, they don't really base it off base 10, they base it off 20. However, there's a slight twist. So in the first position, well, if what we normally consider to be base 20, we would say that the first position would be a 1, and then 20 to the first times something plus 20 to the second times something plus 20 cubed. We would consider something like that. But in the Mayan system, they instead did this. They did the first position was their ones, then they did the 20, then where we would consider it to be 20 squared, they did 20 times 18, or to generate 360. So we sort of surmise that it was based off calendars and what was considered to be unlucky numbers. Yeah, so 360 is the length of the calendar year, plus an extra 5 unlucky days, I guess. I don't know which days would be considered the unlucky ones. But when we look at their place value, so we still multiply by 20, but when we get to the third position out, we're going to add in this extra factor of 18 times something, and then 20 squared times 18 times something. Okay, so that's one interesting change. Another interesting change is instead of going horizontal, they actually went vertical. So here's an example of a Mayan number, and we're going to translate this using this idea of place value. So down here at the bottom, these lines would represent, let's see, so each line is 5, so this would be 10 times 1. Well, that part's 10, yay. Then here we have 13 times 20, and that would work out to 260. And then here's where it gets sort of different. The 3 dots would represent 3, but instead of 20 squared, it was 18. 18 times 20, which works out to be 1,080. Then up here, so before we look at the symbols, it would be 18 times 20 squared. So where we think 20 cubed should be, they would do 18 times 20 squared. And then this would be, what is that? 5, 10, 15 plus another 3, so that's another 18. And that would count as 129,600. And then this last position again would be 18 times 20 cubed, and that would be a 1 there. So I just have to multiply that out. Okay, and then from here we just add up these numbers, and that would translate into 274,950. So this Mayan symbol would be that number for the 274 for us. Okay, in the Roman system, we still have this idea of place value. As you can see, we've not only added symbols for 1 and 5, but now we've included powers of 10, which allows us to change some interpretation of place value. So if you notice in this bottom chart right here, you can see if a smaller symbol was placed after a larger symbol, that actually meant to subtract to get the value of that particular place. So xi and ix are two very different things. So not only do we have place value to look at, but also we have subtraction to look at. And generally, wouldn't necessarily say base 10, but they use the place value and this idea that they could get to 5 or 10 very quickly to work out what the value of a particular number is. So let me get a number up here, and let's see, probably should also comment on what the line on top meant. In the initial Roman system, that was how that was all the access to symbols they had, and then somewhere in the Middle Ages they added this line on top. So with the line on top, that would represent 1,000. So that would be 5,000. If we did something like CDX with the line on top, okay, so we have an extra factor of 1,000 in there. Now CD represent the C would be, well, the D would be 500, but the 100 before it, preceding it, means it's 500 minus 100, so it would be 400, and then the X at the end means we're looking at 10, so we have 410 times 1,000, or 410,000. Okay, so anytime we see. Okay, so let's translate this Roman numeral into our numerical system. So again, we're just looking in order of where we see things. So I see a 3 here. Sorry, I see a 3 here, a 5. That's a 20. The L would be another 50. Let's see, and then I see a C and a D. The D would represent 500, but with the C in front of it, that means we're subtracting off 100, so that means 400. And then the X and V with a line on top, let's see, that would be V, the line on top would be 5,000, and the X with the line on top would be 10,000. So 10 times 1,000. Okay, so putting that all together, we have 10,000, so 15,400, looks like 78. 15,478 is what this would translate into. Okay, so from here we're going to look at just other number-based systems. These aren't necessarily culturally founded, but after a while someone just gets creative and thinks, wow, what would it look like if it was, say, base 5? So base 5 is the first one we're going to look at. That's something that's a little understandable to us. If you look down at your hand, you see 5 fingers. And so you can think of this in terms of how many fingers versus how many hands could we break this up into. So let me just kind of go down here. So let's say we have 1 hand and 1 finger. Well, for us, we would consider that to be 1 hand would be 5 plus the 1 finger plus 1, so that would translate into 6 for us. Okay. Whereas in base 5, they would write that as 1, 1. So 1 hand, 1 finger, the second position representing hands, and the first position representing fingers. Here, in base 5, they would say that as 1, 4, so 4 fingers and 1 hand. For us, that would translate into 9. So let's take a look at a number. Okay, so let's take something like 11244 in base 5, and let's translate that to something that we would understand as base 10. So what that means then, going back out to the furthermost position, so this 1 would mean 1 times 5 to the 4th power plus 1 times 5 cubed plus 2 times 5 squared plus 4 times 5 plus, well, 4 times 1. Okay. And then we just type that in the calculator and see what we get. So 625 plus 125 plus 2 times 25 plus 4 times 5 plus 4. So that's 625 plus 125 plus 50 plus another 20 plus 4. And that'll give us a grand total of 824 is what we would consider that number to be. Let's go the other direction. Let's take a number that we know. So 1,306. Sorry, 1,236. My bad. What would that look like in terms of base 5? Okay, well, what's the? So let me kind of make a list of base 5 powers, and this will kind of help us see what we start off with. All right, so that's 5 to the 0th obviously is 1, that's 5, 25, 125, 625, and I am just going to a calculator here, so 3,125. Okay, so 1,236 is obviously less than 5 to the 5th power, so how many times does 625, so 1236 divided by 625 is 1.977. Okay, but it goes in there one time, right? So for 1 times 5 to the 4th plus, now what I want to do is I want to subtract off, because it only went in there one time, so what was the remainder? So 1236 minus 625. I get 611. Okay, so now what I want to know is how many times does, so now we're looking at the next position, so how many 5 cubes can I fit into 611? So what is 611 divided by 125? And it goes in there 4 times evenly. So then I want 611 minus 4 times the 125. Let's see, so that'd be 4 times 125 is 500. So that's 111. Okay. So then I want to know how many times 5 squared go in there evenly. So obviously 5 squared is 25, so 111 would go in there 4 times with how many left over? So 111 minus 100, we now have 11 left over. Okay, and how many times would, so now we're on 5, so how many multiples of 5 can I get to go into 11? Well, 2 times 5 is 10, so 2, and then how much is left over? A 1, right? So this would translate, I'm looking at these main digits right here, to 14421 in base 5 would be the same as 1,236.